This morning I'm here to give you hope. So, so I'm going to try to write this high-performance computation wave that was launched this morning in the keynote. And so hope is a package that we've been working on for a while. It's a just-in-time compiler that we developed for astrophysical and cosmological applications. But things evolve, things change, and by now I'm aware of other projects that are using hope beyond this niche where we're initially targeting. So in the next few slides, I'm going to give you an overview of what the motivation was for this work, what was driving us to write the just-in-time compiler. And in particular, I'm going to show you two different applications where we are currently working on and where we're using hope every day. And then the second part, I'm going to go more into detail what hope is and how it works under the hood. And at the very end, we're going to see if it's really worth going through the hassle of this JIT compilation. So let's get started. So the motivation, I guess it's no big surprise. Python has evolved to become the #1 language in astrophysics or cosmology. And there are different, very good reasons for that. So I guess it's obvious for most in here. The language is super flexible, so it allows us to write applications very quickly. And on the other hand, we have this wealth of fantastic libraries that guys here at the conference are working on that help us so much to work on our science and make everything easier. So we have a language that allows us to do fast prototyping and develop applications very quickly. But there's a catch with Python. We saw it in the keynote this morning. It's a dynamic language, and it's nice to work with, but it has a price. And the price is that it can be slower by orders of magnitude compared to another compiled language like C or Fortran. So what can we do if we want to go beyond prototyping and we need the speed for our application? So it turns out, we already heard kind of this morning in the keynote, we have different approaches to get the speed that we want. So the first one is parallelization. So we're going to make use of the multi-core CPUs that we have. So we all have a notebook with many cores. We can make use of them. Or if we need even more speed, we run our codes on clusters, so even on the cloud. The problem there is, if the code is slow, it's going to be slow n times, right? So there's an alternative and complementary approach to that. And we can work on the single thread performance of our code. And there are different ways that we can explore. So the first one, we can take our Python code, rewrite it in a native language. We can pull out C or Fortran and rewrite everything. But while we're Python developers, I guess if we can, we try to avoid that, right? The second option, we can switch to a faster Python interpreter. So we can leave our C Python interpreter that we're using all the time and use something like SciPy. There are some catch there. We might get better speed, but some of our science hacky codes might not work on SciPy, and we might not get the full performance that we're targeting for. And the last angle that we have to improve the performance of the single thread is we compile the Python code. So there are two different ways to do that, and we heard that this morning in the keynote. So one way of doing that, and there are many projects working on those two aspects, is compiling ahead of time. So we translate the Python code into something that can be compiled before it actually gets executed. And so we compile it, we get a binary, and then we run the binary and get hopefully the speed that we want. And the other approach, the second one, this is the approach that also Hope is taking, is compiling just in time. So we compile the code when it's necessary, targeting the maximum speed of a single function that we really want to optimize. All right, so we want to get better speed, but what are really the applications that we're working on in our group that motivated this work and we had the need for an own JIT compiler? So the first one of the two examples that I'm going to show you is a project I've been working on the last couple of years. It's a really cool project that I like a lot. And it's the analysis of radio data that we have been collecting with our radio telescope. So you see the telescope. It's a relatively small one. It's a 7-meter single-dish telescope that we operate by ourselves. It's in a beautiful place. It's called Blayen. It's on the countryside in Switzerland, actually not so far away from where I live. So you see, it's fantastic to work there. It's a rather old telescope, and we have been working on the hardware. We've refurbished the hardware. We replaced the instrument, and we're currently using it for some experiments. But it's old, and it was like almost 4 decades ago. The location was chosen not only because it's beautiful out there, but because it was fairly remote, so far off from any civilization. But things change, and people have started to leave the cities and live on the countryside. And we actually see that. So the little house there, that's a farmer that lives there with his family, and they use electronical device, and that gives rise to a certain problem, and it's called radio frequency interference. So that's a signal that is man-made and that is interfering with the signal that we would like to record from the sky. And in our case, we're observing the sky in a particular band, and we suffer from contamination coming from GSM mobile, so your mobile phone and the antennas, of course. And much more severely, we are suffering from aircraft navigation and communication systems. So the aircraft are flying through our beam that we're recording, and it's interfering with our signal. So just to give you an idea how that looks, I tried to visualize the data that we're recording. So in that plot, on one axis, you have the time. On the other axis, you have the frequency. And so you see this underlying wavy plane. So that's a signal that we've been recording from the sky. And if you know where to look, the galaxy was passing through our beam. So the galaxy is one of the strongest sources that we can record with our telescope. And you barely see it because we have this spiky signal all over the place. And this spiky signal is this RFI, the signal that we don't want. So it's pretty clear that we need to get rid of those spikes so that we can use the data for our science. And luckily, there's a very good algorithm. It's called sum threshold. And it's pretty good at detecting and flagging those spikes, this RFI that we don't want. But there's a problem. It gives rise to different challenges. And by construction, this algorithm is iterative. So it looks at pixels. So it's a pixel-by-pixel algorithm. And it looks at the pixel and the neighbors of neighbors of that pixel and detects certain statistical properties and decides if this is either a good signal or an RFI signal that we want to flag. So that's a problem because it's iterative, so it's a lot of nested loops, and we know that Python is not going to excel when running code that contains a lot of nested loops. Another thing is the algorithm requires us to do a convolution of this plane with a certain kernel, and since we are masking part of the signal, we have an array with masks, and it's going to be hard to do this convolution in Fourier space, so we do it in real space. And again, that means that we have a lot of loops. So the challenges here with the radio data analysis is the iterative algorithms that we're using, that Python is going to be intrinsically slow with. The second example that I have here that we've been working on is in cosmology, we want to study the evolution of the universe. What we do there, we have a numerical model that is describing how the universe evolved from the very beginning, from the Big Bang, how it expanded and evolved over time to what it is today. So we have a model. I'm not going to go too much into details. That's not my field of expertise here. But this model is based on a set of equations that are called the Einstein-Boltzmann equation. And essentially what those equations are, it's a set of like roughly 300 or more coupled ODEs, so ordinary differential equations, that we want to integrate numerically. So this model that we have here depends on a certain set of parameters, and we want to study how those parameters affect the result of this numerical integration. And because this is a very time-consuming process, we run this exploration of this huge parameter space on a cluster to speed up the computations. So that gives rise to a new set of challenges. First of all, we have this set of really complex equations, and we're numerically integrating them. And depending on the physics that we simulating right at a certain time, those fields that we're simulating start to oscillate like crazy. And for those who have been working on numerical integration, they know that this means when we're evolving over time, we have to reduce a time step that we take from one moment in time to the next one to really, really tiny steps in time. And what that means, we're going to call the same function over and over and over again. And so we need to make sure that the overhead of calling the function is really, really small. And as I said, we try to do that on a cluster. And working on a cluster is less fun than working on a notebook. So we're working on a constrained environment. Everything's a little bit harder on a cluster. And of course, we're scaling out to hundreds and thousands of cores. So we want to make sure that this is going efficiently. All right, so here's the motivation. We heard that we have different challenges that we try to tackle. And that gave us the motivation to work on this HOPE project on our JIT compiler. So what is it? So the JIT package is a very specialized just-in-time compiler that we developed for those numerical problems that we're seeing. So to be very precise, it's a method-at-a-time JIT compiler. And we've been working on that thing for a while. So the first release was back in 2014, and we have constantly continued to develop new features. And as I just said, we are focusing on a subset of the Python language, and that's the subset that we need for our numerical computations. So we're, of course, supporting all the numerical operation that you would expect, plus, minus, etc. All our codes are obviously based on NumPy, so HOPE understands how to deal with NumPy arrays. We can create new ones. We can slice all the syntax that we like with NumPy. And we're also supporting a small set of NumPy function that we're using relatively often. So HOPE is able to run in different environments. So it supports 2.7 and Python 3 to some extent. And we're currently using it on OS X, so when we're developing on our notebooks, but it runs also on Linux, so when we're scaling out on a cluster, it runs there as well. So it's very important to note here that HOPE is targeting maximum speed. So we only support the stuff or the subset of the language where we know we can compile that and we're going to get the maximum speed there. All right, so how does it work? Let's have a closer look at the nitty-gritty details under the hood. So let's say we have a function that we want to speed up. So it's a function that's taking two parameters, x and y. And what we're going to do then is to speed it up, we're going to import the entire HOPE API. So from HOPE, import JIT, that's it. And that's the entire API. And we're going to decorate our function with the JIT decorator. What HOPE is then able to do is it's going to inspect your function, it's going to parse your code, and it's going to represent that code into something that is called a Python abstract syntax tree. So for those who don't know what an abstract syntax tree is, it's essentially a data structure, a tree data structure that is representing all the operation of your code in a nice way that can be processed by a machine. So what we're going to do next is we want to call that function. So we're going to create two NumPy arrays, x and y, two floating point arrays, and we're going to call that function. And up to now, Python is a dynamic language. Up to now, the data types were not set. So it's a dynamically typed language. But now that we call it, we get information what the different types of all the operations are going to have. So we infer the data types. We combine the input with the Python abstract syntax tree, and we get something that we call the HOPE abstract syntax tree. So it's a strongly typed version of the previous tree that we had. Now that it's strongly typed, we can do really cool stuff with it. So we have the tree. We're going to walk through the tree structure, and from that tree structure, we're going to generate C++ code. And then we have a file that we can compile, and at the end, we're going to get a shared object library that we can use for our purpose. So why are we using C++? There are other projects that are doing similar stuff, and they use something else that might be a bit like advanced. We decided to go for C++ because when we develop a new feature, we're going to produce something that is actually human readable. So if it's not working as we expect, we can inspect the C++ code, and it's going to be much easier to detect the bug. And when we compile it, we can rely on compilers like Clang or GCC to do all this optimization that we want to get the full speed. All right, so we have this shared object library. So what we're going to do next is we cache it, so we write it to disk, and we're going to use it later on. And eventually, we're going to run, and we end up with science, and hopefully faster. And the next time you're going to run your code, we go directly to the cache, we load it from the file system, load it into memory, and run it directly. So we don't have to go through this cumbersome parsing of the tree, and we get even more speed, right? This is a very important aspect, considering that we want to run the code on a cluster. So we want to avoid that we have thousands of cores recompiling all the time, right? All right, so that's the overview. Let's dive a little bit into more details. So we have this Hope abstract syntax tree, and what we can do, we can inspect it and do something that is called loop fusion. So let's assume we have an array, we do multiple operations on it, we're going to detect that in Hope, and we're going to fuse them into one single loop. So instead of looping multiple times over the array, we're going to do it once, and we avoid to do multiple loops. Another thing that we can do is we work with SciPy. So for those who don't know SciPy, it's a symbolic math library. It's fantastic. It's really cool. You should check it out. And what we do is we take this Hope syntax tree, abstract syntax tree, translate it into something that SciPy understands, and we're going to simplify your equation on the run while we're compiling your application. Another cool thing that we can do is, it's called common subexpression elimination. So SciPy is going to look at your equation, detect if you have patterns that occur multiple times. It's going to externalize that. We're going to make sure that we compute it only once, and we're going to reuse the temporary variable in your equations. So we're going to save time there as well. There are other cool features that we use SciPy for, but I'm not going to go into more details here. So once we do this optimization, we get an optimized Hope abstract syntax tree, and the rest remains the same. So we generate again the C++ code, compile it, have the shared library, and we're going to run it. So now you've seen how it works. I hope you might have seen some application that might be similar to what you do. The ultimate question is now, is it worth going through this hassle? So on the next slide, I'm going to show you some benchmarks. Andreas is not going to be happy. It's not very scientific, I guess, the benchmark that I did. It's a benchmark in quotes. It's not entirely fair. It's absolutely clear. But for our first case, so where we had the radio data analysis, I measured the runtime of the pure Python code, and then I JIT compiled it with Hope, and our code was then running faster by a factor of 200. It's pretty fast, but it's kind of obvious that we get this speed up because Python is super slow when it comes to nested loops. In the second case, where we're studying the evolution of the universe, where we are having those ODEs that we were computing, so when we compare the pure Python code to the JIT compiled one, we get a speed up of a factor of 38. And the second comparison is we have the JIT compiled version, and then I enabled those symbolic optimizations, and there we get another 5%. So it doesn't sound like much, but it's 5%, it's for free. And to be fair, we already tried to optimize the equations a little bit before we JIT compiled it. So if you like what you've seen here, Hope is on PyPI, just run pip install Hope. We have more information, background information, and a reference to our paper on the website. We have documentation on read the docs. The code is hosted on GitHub, so if you like it, check it out, and thank you very much.
Time for questions?
Yeah.
Can I see the next last slide, the backward slide?
The performance?
Just the improvement. Okay, what
So the question is, what was the optimization when I went from the normal jig compile to jig compile plus the optimization? Essentially, that's running the common sub-expression elimination, so making the equation simpler and reusing some of the terms in the equations. And
Kind of similar to what Tino talked about.
I'm not sure if he's doing also something similar.
I mean, parts of it were difficult. Anyway, okay, thanks.
Thanks. Another question?
Have you compared this to, say, Numba or?
Yes, we did. So I guess that's a fair question. Why aren't we using Numba? So we started in 2013. At that time, Numba wasn't at the point that it is today. And when we did our first release, we had a comparison. In some of the cases, Numba was not able to jig compile the code that we were benchmarking. If it was able to jig compile, it got like similar speed, and in some cases it was faster. Sometimes Hope was faster. So.
Have you interacted with that team at all in terms of shared experiences or?
Yes, we have interaction. In fact, we just had a little workshop before SciPy where we try to exchange our notes. Yes?
Along the lines of what we heard in the keynote today, what kind of parallelism or SIMD type optimizations are you either using now or hoping to incorporate into the code you're generating?
So at the moment, we don't have any support for SIMD operations. Might be worth to consider, but I guess that would require quite some changes in the code. And as we seen this morning, it's pretty hard to take a random code and turn it into something that is SIMD ready. Let's put it that way.
Any other questions? All right, well, thanks very much. Great talk.
Thank you.